So where we stop, we were calculating. Can you change this? I don't call this stress max. I like to call this stress 1. Okay. So we are calculating the minimum and the maximum stress. And this is our stress 2. Stress 2 is minus 7.5 plus by 20.736. Okay. So that's because it's the center of the circle. You are finding the diameter of the circle or the extreme position of the circle now. So this will be equal to positive 13.236. So now we can more or less sketch most circle. Okay. And then when we sketch most circle, so the minimum is 28.236. The maximum is 13.236. 12, 13. So it's about here. Okay. And then you have 20. Your shear is 20.736, so somewhere about here. And this is 20.736, somewhere about here. Okay. So this is only one circle. So this circle touches point Y and point Z. So we call this, bless you, sunshine. We call this the circle for the YZ plane. As I told you, there are 2 more circles. Okay. So one circle, so over here, this is your stress 1. Over here, this is your stress 2. Then you have 2 more circles. So one circle is from point X to stress 2. So one of the circle will be from stress X to stress 2. Okay, so you know the extreme diameter or the extreme position. So you just need to draw the circle now. 2, 4, 6, a bit 7, 3.5. Okay. So 3, 3.5, 3. Hey, it's a very interesting circle. So 3.5. So 2, 4, 6, 6, 3, 3.5. Oh, I did not reach 3.5. Hold on, hold on. Okay, this is just a sketch. So this circle over here belongs to the YZ plane. And the last circle, 2, 4, 6, 8, 10, 12, 14, 7. So the last circle, yes. Oh, no, this is XZ, sorry. This belongs to the XZ plane. Thank you. And the last circle, 2, 4, 6, 8, 10, 12, 14, 7. 2, 4, 6, 7, 7 and a bit. And this is the last circle. 2, 4, 6, 7 and a bit. Okay, don't worry too much. I will teach you how to draw it properly. This is just a sketch. So this is the last circle. And this circle over here belongs to the XZ plane. I will teach you how to label the planes. So class, meet 3D mole circle, 3D mole circle, meet the class. Okay, so this is a full 3D mole circle, as you can see. Yes. Wait, did I label? So this is XZ plane. This is XY plane. Yeah, make mistake again. And the last one is YZ plane. Is it okay? Thank you for spotting mistake. I'll buy you a pint of orange juice. I know you don't drink. Okay, so this is a 3D mold circle. Are we clear? Okay. Now, as you can see, the maximum value is what? 28.236 for element B. Element A, the normal stress is already what? 29.658. So the highest stress will be on what? Element A. Are we clear? Okay. The next problem I'm going to do is a problem that is not straightforward. Okay. And I love questions like this. Question like this makes you become a competent engineer. Okay. So this is example number 2. So example number 2, the diameter is equal to what? The diameter is equal to 60 millimeters. Okay. So what we're going to find is determine the position of maximum, or determine the position where failure will occur. Okay. So this is like an actual engineering problem that you will get. Okay. Determine the position where failure will occur. And you can see, will failure occur at element H? The answer is no. Element H is not going to be where failure will occur. Can someone tell me where failure will occur? Which plane? At A, yes or no? Can you see that? At A is where failure will occur. Okay. So first thing we have to do, okay, we have to look at the plan view. So we have our transformation. So this is our X, this is our Y, and this become our Z. And if we were to look at the plan view, okay, this is our plan view, okay, and this is our geometric centroid where failure will occur, right? And then you can see down there in our diagram, this is labeled at A down here, okay? So I'm going to address the element, okay? So this is our elements. Before I go on, I will sketch out the transformation. So this will be our X, and this position over here will be our Z. Now this is relative to the transformation that we see on the diagram. Then we are going to position 4 different elements. Element I, element J, element K, element L. So this is our element I, element J, element K, element L. L, I'm going to use a capital letter. Okay. When I say, oh my gosh, I'm like way off today. IJ, I need to move it. Okay. Can you see that now? Now, why do I position the elements there? Why don't I position the elements in a diagonal way? Anyone? I position the elements there because it's relative to the bending moment. And I position the elements there relative to the bending what? Questions like this, you need to analyze where what? where failure will occur. Okay. If this question were to come out, if you analyze the right element, you get full marks. If you analyze the wrong element, we just minus you 1 mark. Are we clear? Okay, so we want to see whether can you identify where maximum failure will occur or which element. So which element has the highest stress? For now, I have not a clue. I don't know. Okay, now coming back to our diagram over here. At point D, this question looks very innocent, but it's not. Are we clear? Like you and me, looks innocent, but we are by no means innocent. Okay, so from here, maybe Evans is the only innocent one. Evans, you here? So you study hard for term. Are you taking term this term? Okay, good boy. Woo. So over here, you have your what? dy. So you break it down to your components, and then you have your what? Over here, you have your direction, and this is your what? Ez. Yeah. So now we are going to determine our components. Dy and dz. Okay. Before I go on, for now, I have not a clue where which element is under the higher normal stress and what? The higher shearing stress. I have not a clue. Yes. The Y is coming towards us, so I did not draw it. Okay. So from here, there are different ways that you can calculate dy. I'm going to calculate the distance dE first. So dE is equal to what? So dE is equal to 0.3 squared plus by 0.125 squared. Okay, so I'm calculating the length D. I'm going to use similar triangles for this. You can use angle. The answer will be absolutely the same. So this is equal to 0.325. So to determine dy will be equal to 0.3 divided by 0.325 multiplied by 13 times 10 to the power 3. Okay, so dy 13 power 3 times power 3 divided by 0.325 is equal to 12 times 10 to the power 3 Newton. And then you calculate, determine your dz. dz is equal to 0.125 divided by 0.325 multiplied by 13 times 10 to the power 3. 0.125 divided by 325 times by 13 to the power 3 is equal to 5 times 10 to the power 3 Newton. So we know that our dz is equal to 5 times 10 to the power 3. You know our dy is equal to 12 times 10 to the power 3. So from here, we view things from different views to determine. So the next thing we are going to determine our axial forces or axial force is very obvious. This is our axial force. We're going to determine our shear force. We are going to determine our bending moment. And for this case, I deliberately pick this example to determine our torque. So this example is different from what we have before. Is the torque. Okay, previous example, we don't have the torque. This example has the torque. That's why I picked this example. Okay, and also for this case, you don't know where failure will occur. Okay, these are the type of problem you'll get from your co-op. Okay, you see a structure like this, and then your supervisor will tell me where you will fail. Okay, there is no such thing as what? Element H. Are we clear? Okay, this is real life. Right, so from here, we are going to now view this in the XY plane. So now we are going to sketch the XY plane. So this is our X, and this is our Y. And then if I zoom out a bit, this is a sketch, and this is how it looks like. At the same time, you determine the position of your geometric centroid relative to the point of interest. Okay, so this is where the centroid is. Okay, then from here, to ease your mind, start labeling where your elements are. So from here, we know that over here, this is your element I. Over here, this is your element J. And over here, this is your element L. So what is given to us is we have a load coming down. So that is our dy. dy is 12 times 10 to the power 3. And then we have a load going away from us, and this dot is at 5 times 10 to the power 3 Newton. So from here, we know that we are going to have a what? We are going to have, so if I'm going to, this is X, Y. So this is our rotation about Z. So from here, we know that we have a moment about Z. Moment about Z will be equal to 12 times 10 to the power 3 multiplied by a distance of, okay, so the distance is 0.15. So let me put in the geometry. The distance from here to here is 0.15. Okay, so the applied force is parallel to the what? Centroid